All right, from your science classes, how do you define force?
Force, mass times acceleration.
Okay. Force equals mass times acceleration. It's the famous F equals ma equation. Okay. For an object that's not moving, okay, just a still object, that force is the same as its weight. Okay, if it's just not moving, assuming we're in an environment where gravity is pulling on that. So those are measured, force is measured in pounds or kilograms or newtons or whatever. Okay, work. Work is the integral of force. It's the antiderivative. Okay, so if you know calculus, you can figure out work pretty easily, assuming you know force. And so we'll go from A to B over some kind of distance, or it could be, a y, the y-axis if we're moving this thing vertically. Okay, so the definition of work is the integral of force. So your job is to find the force equation and then simply do the math on it to integrate that. Okay. So the idea is the work is required putting a stationary object into motion. Takes work. And how much work does it take? Well, you integrate force. Putting a stationary object into motion. So we got to talk about some units so that we understand what we're talking about. So the metric system. Okay. Distance in the metric system measured in, we'll say, meters. Force measured in something called newtons. And then work is the combination of those two. So the unit for work is something called a Newton meter. But there's also a different unit that's synonymous to that, okay, and it's the word joule. Joules, spelled not like diamonds and rubies and sapphires, but spelled Joules. So a joule is a Newton meter. A Newton meter is the multiplication, the combination of the unit of force and the unit of the distance that you're moving that on. Okay, the American system. Does it have a name?
Imperial.
What is it?
Imperial.
Imperial. Are you sure? Maybe. I don't know. I thought it was the empiric method and the imperial. I thought it was E, but it's I. All right. The imperial system. So in the imperial system, distance is measured in feet. That's our common unit. Force is measured in pounds. What kind?
You're wrong.
It's the same thing.
They're the same? What is it called? Customary to who? To us in the United States. What? Yeah, there's I think one other country that uses it besides us. It's like American Samoa or something like that. It's all right. Customary imperial system. All right, well, either way, what are we going to use as our unit for work then? If distance is feet and force is pounds? A foot-pound, right? It's the combination of those two. And that doesn't really have, as far as I know, any interesting other synonym for it. It's just a foot-pound. We're going to measure that in foot-pound. All right, so there's our units, and there's our definition of work. The definition is pretty easy. As with like a lot of these things, like when we were doing related rates, and when we were doing cross sections, the calculus part is not the hard part. What's the hard part? Setting it up, right? So the hard part is going to be setting up the force equation. The easy part will be integrating it to get the work. Okay. All right. So here's a classic example called the leaky bucket problem. If you Google calculus leaky bucket, you'll get all kinds of videos of people solving this and, you know, diagrams. And but it's like the sliding ladder problem. It's just one of those classic problems that is used to illustrate something. So this is called the leaky bucket problem. All right. A bucket weighs 22 newtons when empty. It's filled with water and now weighs 92 newtons. Okay, a rope is tied to the bucket to lift it up. The rope weighs 2/5. How about we do it like the app? Right? All right. Look at how many ways we could spell weighs. Okay, the rope weighs 2/5 of a newton per meter and is 20 meters long. Did I write that down right? Okay. As the bucket is lifted, there is a leak. Okay, and so water leaks out. And times it perfectly to be empty when it reaches the top.
Wait, I thought you were going to say it was going to have an exact correlation with the weight of the rope, so we would have to calculate the calculus of the work.
Oh, well, when we get to the end of the rope, We get to our bucket, now there's no water in it. It's all gone. Bummer. Yeah, right. There's a hole in my bucket. Do you guys know that song? Dear Liza, hole in my bucket. All right. The calculus is easy. Okay? The setting up is hard. Let me show you. Let's break this down. Okay. All right. Oh, the question. How much work was How much work was done? All right. I went over and over and over the best way to organize this, and I think I got it. All right. What is contributing to this problem? To the what objects is the work being done on? The bucket, the rope, the water. Okay. So we've got. Let's organize ourselves that way. You want a separate integral for each one. Don't try and like make one big massive thing. Okay. Let's just do separate. All right. We've got the bucket. We have the water. We have the rope. All right, let's start with their initial weight. Which is the same thing as force. Initial weight, force. All right, what is the initial weight / force of the bucket? All right, 22. What is the initial weight / force of the water? Okay, what is the initial weight / force of the rope? 8. How'd you get that? Thank you. Okay. Very good. All right, now, which of those doesn't change the entire time? Okay, the bucket doesn't change. All right. So our question of whether it changes, the answer is no. So then the integral is simply the integral of 22, because that is a constant and it is not changing for the entire length of the rope, which was? No, that was the weight of the rope, the length of the rope, 0 to 20. So for the entire length of the rope, that bucket never changes. So there's its integral. Okay, the integral of force is work. So all we had is one force, and it was 22. All right. Now, the water is changing. Okay, the water is changing in such a way that by the time I've covered 20 meters, it's now empty. Can you figure out the rate at which the water is leaking? If it started out with 70 and is now gotten down to nothing after 20 meters.
70 over 20.
70 over 20. Right? 70 over 20, which is? 3.5. Okay. So the bucket is changing, or the water is changing in the following way. It is 70, and it's leaking out at a rate of 3.5, or 7 over 2, x. Okay? So we integrate that too. So that will be 0 to 20 of 70 minus 3.5 x dx. All right? And we're going to do the same thing with the rope. All right, so my rope is getting shorter. At what rate? Which is 0.4. Yeah, 2/5. That's the Newton meter. A Newton per meter is the rate. Okay. Okay, so we need an integral for that. 8 minus 0.4, or 2/5 dx. So rather than try and figure out one big equation that's going to cover everything, just look at each individual component and come up with an integral for them independently. All right, so then the work for each of those is the answer to the integral. So the answer to the integral of 22 from the bounds from 0 to 20 is 440. And what are the units on the work if this is the type of problem okay, J for joules, be fine. Okay, the next one, I've already worked it out for us. It's 700, J for joules. And then 80 J for joules. And so the question is, what is the total? So we just add those up. Okay, yep, 1,220 joules of work. The calculus was, I did the antiderivative, the integral.
But we don't even need the
Because these were constants. Yeah. When it starts to be changing, then you need the calculus, like a changing rate. But it's the constant rate.
Are we ever gonna have that?
It will probably give it to you as the force. Here's the force equation, blank. Okay, give that to you. All right, let's try another one. Okay, so that's sort of the. You will, because then you're going to be asked in your homework to do the same thing, only you're going to be filled with maybe oil instead of water. So the only thing that will change about this is because oil has a different weight than water does, right? If you've ever tried to mix the two. Yeah, okay. Or maybe you'd be given a bucket made out of plastic instead of a bucket made out of whatever this is. So you're going to redo this problem. Yeah, you're going to... Yeah. Okay, just because of the components. So they'll change some variables. Or they'll say, well, what if there was no leak? Okay, what if there was no leak? Then how much work would you do? So then the only thing that would be changing is the rope. Okay, so they're going to give you some different variations of this question. Okay? Yeah. Usually it's filling with something, a different kind of liquid or fluid. Okay. 2 plus a definition? Not quite. It's raining again. All right, next one.
Same. I was like, we just need that extract the fields need to flood, flooded. Yes. But then she'll just find it on the grass.
Okay, so you have the leaky bucket problem, which is a famous problem. Now you have the spring problem. Not as in like a spring of water, like a spring as in a spirally bouncy spring, right? Like a Tigger. Okay, and we need Hooke's law for this. Mr. Hooke. So let's start with Hooke's law.
Like I thought that was his name, like Hoopla.
Oh, no,
Like,
Hooke.
Like,
Hooke is the guy, and this is his law.
yeah, see, that makes more sense.
Okay.
That was his whole last name.
All right. So his has to do with force as it applies to the spring. A spring can either be stretched or compressed. Either way, there is a constant, which we call K, which relates the force to the distance. Now there is no one single universal constant like pi, right? Pi is a constant that works on every single circle. Okay, doesn't matter. The constant here is unique to the spring. Okay, every spring, depending on what material it's made out of, or the tension of the spring, has its own constant. Once you know the constant for that particular spring, that will work for that spring whether you stretch it or compress it. All right, but if you moved to a different spring, you would have a different constant for that spring. So that's why we can't give it like an actual Greek letter or anything. We just call it K. All right, here we go. This is how the constant is determined. K is found by figuring out the force and dividing it by it's the ratio of the force to the change in length. Or, in other words, what would F be equal to? Correct. Okay, that is Hooke's law. Well, okay, if you're depends on the change in the length, right? Okay. Okay, well, the calculus is, once you know the force, you can integrate it to find the work. And so once you have Hooke's law that can help you find your force, then you can do the calculus to find the work on that spring. So I guess this is all one example. All right, so here's our spring. Is stretched 2 meters. Using a force 10 newtons. How much work will it take to stretch it further to a length of 4 meters? Okay, so first, oh, don't worry about it. I'll fix it.
Oh no.
All right, first we need to apply Hooke's law because we need to find the spring constant for this particular spring. So K, the constant, is defined as F over X, so 10 over 2, so 5, for this particular spring. So that is the constant. So now I can use that constant, and F equals Kx. In other words, F equals 5x, and x would represent other distances.
Whoa, wait, whoa.
All right, now if we just wanted to find the force to stretch it to 4 meters, we just multiply this by 4, and we say the force is 20. But we want to find the work required to stretch this. And so our work, now that we know the force, is the integral of the force, dx. So we'll have to say, may the integral of the force be with you instead of just the force be with you. So we're going on 5x dx, but what are my bounds?
2 to 4.
No, that would be how much more work it took.
I drew the 2.
Okay, no. Okay, we want to go 0, which is its natural length, to a stretch of 4. Okay,
But,
so not how much.
oh,
Okay. Why did that?
Oh wait, no, I did. I didn't say total, did I? I said how much would take to stretch it farther.
Oh, 2 to 4.
You're right.
Oh. Okay, Ricky.
All right, if we wanted the total amount of work, then we go 0 to 4. We just want to know how much further. Okay, so once you get that, I mean, the math is so easy, right? 5x squared over 2 plus c going from 2 to 4. So that's 5 times 16 over 2 minus 5 times 4 over 2. Or 5 times 8 minus 5 times 2, 40 minus 10. 30 what? All right. Nope, one more.
All right, we were doing it.
All right, last one.
We don't need a calculator.
No, still not.
You just find the average and like find the.
Because it's a constant,
Yeah.
yes. Okay. Now, the other classic example we're going to do is the kinetic energy example. Okay, kinetic energy has to do with velocity. Say that again?
Can I write problems?
Sure.
I mean, like, you don't need to.
I see what you're saying. Yeah, you didn't want to, it's like you can't use the word in its own definition.
Yeah.
All right. So a couple things we need to know. All right, in physics, you may have memorized this example. Somebody in a physics class somewhere told you that work is half of mass times velocity squared. Okay? Now, but it's like telling you, oh, the area of a circle is pi r squared. But then do you ever stop and think, why? Okay. All right. Why is that? Okay. So it's like somebody tells you, all right, there's pi r squared and there's 2 pi r, right? One of them is the area and one of them is the circumference. And you kind of go, okay, yeah, I'm going to memorize that in geometry. But until you learn calculus, you don't understand that, oh, 2 pi r is the derivative of pi r squared. Oh, okay. Or until you, like, the calculus is where all of these things come from. The quadratic formula, I mean, all the volume formulas for a sphere, and where do they come from? They come from calculus. So this work equation comes from calculus. All right, m comes from where? Where does it come from? We've already written that down. So where would m come from then? M would be F over A. Right? If F equals MA, then M equals F over A. So that I can modify my work equation and say it's 1/2 F over A times V squared. All right, here we go. How much work does it take to throw a 5-ounce baseball at 90 miles per hour? Or it's one thing to throw a baseball at about, 30 miles an hour, which is about probably what I could manage. Okay, how much would it take to throw a 5-ounce baseball 90 miles per hour? All right, so here's where we're going to get unit conversion happy. You don't like unit conversion?
How many ounces? Is it 16 ounces?
Yes, okay, so we need to get into pounds. Okay, so 5 ounces equals 5/16 of a pound. Okay, all right, now we need to figure out the mass. Okay. Well, let's see. So I think we've got everything. We've got work equals 1/2 F. Okay, where's our F number here? Nope, that's our V. That's our velocity.
Acceleration 0.
No?
Gravity. Depends gravity.
Okay, we're going to have gravity doing so. That's the A part. Okay, what is F? What are the units for F? Look back.
MA.
Yeah, but what are the... Okay, not in this question.
Oh, pound.
Pounds.
Meter.
Yeah,
The pound feet.
Just pounds.
Yeah, so this is.
Okay, so F over A V squared. F is measured in pounds. Look back at your units. We wrote them down. Okay, F is measured in pounds. We know the pounds are 5/16. All right, acceleration, A. That's what A stands for. Hopefully you know the acceleration due to gravity. Okay, that's in meters. We're doing, okay, 32. All right, and we know velocity. Velocity is 90. What's the problem with velocity, though?
It's in miles.
It's in miles. Oh, can't use 90. Got to change 90.
Is it in seconds? Should it be in seconds?
Yeah, we want to get it into feet, first of all, and we need to get it into seconds. Because why do I have to get into seconds? Because what's acceleration measured in? Feet per second squared. So I need to change my velocity, question mark.
Meters per second?
Feet,
Oh,
feet per second. All right, so 90 miles per hour. Okay, unit conversion. 90 miles per hour is, first, how many feet are in a mile? 5280 feet per mile. Why do I put the feet on the top and the mile on the bottom? Right, okay, I want the word mile to reduce. Okay, now I need to convert or reduce the word hour out. So, and I'll put an hour on the top. How many seconds are in an hour?
36.
Okay, and then the word hour will reduce. So I'll have 90 times 5280 divided by 3600 works out perfectly to 132 feet per second. That is my velocity, which is going to go in for V. So my work, 1/2, 5/16 divided by 32 multiplied by 132 squared, which works out to be 85.08. And what are the units on this if it's work? Feet pound. Foot, not foot per pound, but a foot pound.
Is dash equal to multiply?
Yeah, dash times, you could do foot dot pound. Or an X. But an X might look like a variable X, so maybe you could do a little star or something, or whatever. It's a foot pound. Okay, yes. Again, no calculus.
Yeah, that's the point. Like in the beginning, you said, this formula comes from calculus.
It does. I didn't show you where.
I thought you were going to